Good, so this talk is entitled Exploring Geometrical Shapes and Designs. And as I have already said, that the talk was started by myself putting together worksheets and activities for quite small children. And what we're going to start off looking at today is some very simple shapes like triangles, squares, and polygons. And because we are doing a Vedic mathematics conference today, I would like to start by sharing two sutras in Vedic maths which relate to this particular topic, with the first one being Vilokanam, by mere observation. And just by looking or observing, we can appreciate some intricate designs and patterns, and we can explore various activities that can be done with these shapes we'll be looking at. And by playing with the shapes in the way I'll be showing with you, I hope also to encourage all of you to explore further in this way and come up with your own creative ideas. The other sutra is when the totals are the same, it is 0. And this really refers to the concept of symmetry. So we all know that symmetry can have various forms. One form is planar symmetry. A line of symmetry divides a shape into two halves, which are mirror images. And then we also get rotational symmetry. Each time, for instance, that an equilateral triangle undergoes a 120-degree rotation about its center, we can actually find that it can undergo 3 such rotations during one revolution, and it therefore has threefold rotational symmetry. When we look at this little flower here on the right, it naturally has a 4-fold rotational symmetry. Many flowers have pentagonal or 5-fold rotational symmetry. Most of them actually have that. And even this apple, when we cut through an apple, we see that there's a little pentagon inside the apple because there's a 5-fold rotational symmetry in the way that the seeds form in the apple. We're all very familiar also with the fact that water, when it freezes, due to the way the hydrogen bonds form between the water molecules, we get a beautiful hexagonal crystal structure in ice. The other concept I just want to introduce is the concept of tessellation. A tessellation, or a tiling of a flat surface, is the covering of a plane using one or more geometric shapes called tiles, and there's not supposed to be any overlaps or gaps. Tessellations can also be done in 3-dimensional space or volume. We'll end the talk with looking at some such tessellations as well. So we're starting off very simply, and we're looking first of all at a triangle. Now this is often the first shape that is also introduced to small children. When you've got an equilateral triangle, it of course tessellates. We find we can pack 6 equilateral triangles around a point. This is of course because the angle in each triangle is 60 degrees, and 6 times 60 degrees is 360 degrees. Squares, of course, also tessellate. Most floors which have tiles on are square tiles, and because squares have 90-degree angles, 4 times 90 degrees is 360 degrees as well. Hexagons, of course, also tessellate. The hexagon has a 120-degree angle, so we can pack 3 hexagons around a point. 3 times 120 degrees is also 360 degrees. However, pentagons are very interesting shapes because they don't tessellate. When you attempt to pack pentagons around a point, you can actually only pack 3 pentagons around a point, and then there's a gap. If we pack a few more pentagons together in this way, we start getting quite an interesting little design and the star in the middle coming out. A regular pentagon has a 108-degree angle, So 3 times 108 degrees gives you 324 degrees, which means there's a 36-degree gap. This leads to the fact that pentagons make some really interesting designs, and they have very interesting mathematics related to them as well. So we're going to look at all these shapes, starting off with triangles and some simple activities we can do with even very small children. One thing one often wants is a tessellating triangular grid. And one way we could construct such a grid is by first drawing a circle with a compass, and keeping the radius the same, we can put the point of the compass on the circumference of the circle and draw another circle. And we can proceed around that central point and put 6 overlapping circles and get this little 6-sided little flower inside. And we can actually carry on overlapping circles. I'm sure we've all played like that at some point when we were children and made these kind of designs. Now, if we take a ruler and connect up some points, we can draw 3 sets of parallel lines, and so we generate the triangular grid. So if we rub out the circles, we'll have a triangular grid. And smaller children and also adults like myself enjoy just, if I've got some time, doodling and trying to maybe find if we can find a nice pattern, design a little pattern on this grid. What I often would do with small children is draw a certain pattern out and get them to copy it first. And then I will let them come up with their own creative ideas as well. Here I've colored in some of the triangles in this way, and we get this pleasing mosaic pattern of triangles. One could, of course, just make lots of different colored equilateral triangles and stick them together as well as a group activity for a class, perhaps. Children, of course, also love dot-to-dot activities. So this manuscript I've put together has quite a lot of dot-to-dot activities in with triangles and squares and so forth. If we connect dots together in the following way, we find that we generate a sequence of triangles inside a triangle. So there's a triangle inside the triangle, inside the triangle, inside the triangle. Theoretically, forever, it can kind of zoom inward and outward. This is typical of what we call a fractal. A fractal is a geometric object which is made up of shapes similar to itself, infinitely deep into the fractal. We can color this in. So this kind of activity I've done even with 5- and 6-year-olds. And that it's a very good encouraging them also to work with rulers. And they enjoy it, it's creative, they can come up with their own patterns as well. So this is one fractal-like pattern we can make with triangles. Another activity with dot-to-dots and triangles is the concept of curve stitching or line art. Now, if one proceeds to connect certain numbers together in this diagram here, for instance, 1 plus 17, it's very small, the numbers, then 2 plus 18, 3 plus 19, 4 plus 20, 5 plus 21, 6 plus 22, etc. Once you start showing the children how to connect them, they immediately know what to do. And we start getting this very pleasing curve being generated. Now, I myself wondered, what is the mathematical formula behind that curve? And also, interestingly enough, it relates to Angela Peary's talk yesterday on the Vedic loom. I was thinking about this when she told us the activities that she also does with children. So I Googled a little bit about this and found some interesting articles. This is an article by Stephen Arnold. And if you would like to contact me, I can maybe send you the link around the maths of these line art drawings. And we can show it's parabolic. So let's just go back to what we were doing and connecting these dots together. Then, of course, we could carry on. And so now we get these two interlocking curves, and we could carry on connecting the two top sides as well. And eventually we get this 3-petal design emerging. If the children have made a design like that, if they're very small, we might not have to we can maybe make it with a few less lines. And then you can color it in a certain way and make a very pleasing diagram. If we take one of these triangles and we pack 2 more triangles below it in this way, and then reflect the top triangle downward as a 4th one, we get this shape. So it's just a more intricate, again, fractal-like design which we've made with these curve-stitched triangles. And if I rotate it a bit and paste 2 of them together, then we get this rhombus or diamond which is formed. I haven't colored that one. We can also curve stitch on the inside of a triangle. So if we follow a similar process, once you get children going about this far in it, then they automatically know what to do. Sometimes, of course, they connect the wrong dots together and they might have to start again. It's very good for concentration, and children very often enjoy the beautiful shape which emerges. If you color this one in, I also get now this 3D effect coming through. It almost looks like that red part is coming out towards you. And can one tessellate with these shapes? I tried pasting some of these shapes together around a point, and we could carry on putting them together in this way and get quite a pleasing kind of a grid design coming out. Here's just 3 of them pasted together around a point. We can also put 6 of them together around a point and make this diagram. And now we see again the 6-petaled flower emerging. I've put a few more of them together. And in the next slide, there's a bigger one which I haven't colored in. But here we also see definitely a hexagon emerging. 3 and 6, of course, go together. So now let's do a few similar activities also with squares. We're all very familiar with a square grid. And you can color in blocks in a certain way and make quite a pleasing tiling design with squares. Here's one more I played with. Just reduced it a bit, made some symmetrical square patterns here. So just colouring in is also fun to do. Dot-to-dot activities with squares. If we follow a similar curve stitching mechanism around a square, we get almost this kind of an eye shape emerging. And we could carry on connecting the dots and get this 4-fold petal diagram emerging. In this slide here, what I've done is I've made this initial one a bit smaller and then pasted 4 of them together. And then we get this more intricate design which emerges as well. We can, of course, paste many of these ones together as well. I made these designs on my husband's AutoCAD software program. He's an engineer, so I'm lucky to have that facility to be able to draw out these shapes. But of course, for children, you could just give them a piece of paper with a printout of the dot-to-dot diagram, and the activity would be to connect the dots together. Here's again a more internal curve stitching on a cross. We again get this square design, which we can also colour in, get this 3D effect again. I also reduce this one and pack some of them together, and we get this design emerging. almost circles between these four-sided designs, but not quite. Here's a few more ways you can pack these together. So a class could each make one, and you could put them together, perhaps on the wall somewhere or on a larger piece of paper. When many years ago, one of the first times I met James Glover in England, I would say more than 20 years ago, I met a teacher there who showed me the following design you can make with squares as well. If you draw out 6 lines which all pass through a point, and in other words, you divide the point into, around the point, there's 12 equal angles of 30 degrees. And then we proceed to draw diagonal squares as shown on the right. And say these squares are 1 by 1 squares. When we connected the diagonal of one of these squares, that length would be the square root of 2, so an irrational number. And if we take that diagonal and swing it out by 60 degrees, and also do it to the square next to it, we can proceed to generate a second square in a layer above this layer of squares, and carry on drawing these kind of squares, so we get a whole second layer of diagonal squares around the first layer. And then we could follow the process again and generate a third layer in the same way. And if we carry on long enough, we could make this very beautiful design, which can be colored in different ways and brings out different properties of this particular infinite looking kind of design. The first way I've colored it is only with 3 colors, and we see the spiraling outward forever and spiraling inward forever effect. It also looks like there's 3 sets of colored squares just kind of rotated around each other. You can also color it in a way which brings out a hexagonal and also a triangular symmetry. Good, and then I'm sure most of you are familiar with the artist called M.C. Escher. He was a Dutch graphic artist and is very famous for his so-called impossible constructions. You have these people walking upstairs forever but not getting anywhere. And he also made some very beautiful tessellation designs with birds and reptiles and fish. This is one of the designs he made. So it's completely interlocking birds and fish, and it fills to a plane completely. So one can do this kind of activity with a class as well. Starting off with a square, you can cut out some little design at the bottom of the square, cut it out and move it and paste it at the top. And then on the left, we can draw another little design, cut it out and go and paste it on the right. And then we can maybe put a little eye on it, and we've made a funny little fish. So if each child in the class makes a fish like this in different colors, we find that they tessellate in a plane completely. So if you fit them together in the following way, we see that they will fill a plane completely. So one can just do this with colored paper as well. So here's a typical Escher design. And if one plays with this, I'm sure you can also make birds and fish. So 2 kinds of shapes if one investigates how to do this process properly. And just to end the squares and triangles part of the talk, how about trying to tessellate with equilateral triangles and squares? So I've put 6 equilateral triangles together like this, added some squares which have the same length size, and we can fill some triangles in there, perhaps add some more squares on those triangles, put some triangles in there, fill in the gaps with more triangles, put some more triangles on the next layer, some squares. Actually, we can do exactly what we like, maybe end up with a design like this. I just had some fun putting different sizes of these designs together to make this set of patterns. And if we go again to this original uncolored design, you could actually keep on adding or pasting triangles and squares together forever. So here I've gone further, I reduce it a little bit, add more triangles and squares, and what we see now is a hexagon emerging. So triangles and squares can pack together to make a six-sided shape. If I proceed even further, one could eventually end up with a shape like this, which is now a little bit more intricate. It's got some curves, but still we see a hexagon has emerged. So let's move to the topic of six-sided shapes or hexagons. So hexagons, a grid of hexagons, we can make with the same set of interlocking circles, except we go and draw out the hexagons we see. So by mere observation, we can do this. And if we rub out the circles, we can get our set of our hexagonal grid, which perhaps if we make it a little smaller, once again, one could draw out color in these hexagons and make some type of design. With smaller children, I would draw out my own design first, perhaps a very simple little design, and get them to copy it. So they look at what I've done, and then they would copy it. And then their confidence grows, and then they can become more creative and make all kinds of other designs. There's an infinite number of designs you could do, of course, the hexagonal grid like this. Dot-to-dot activities with hexagons. If you just connect the vertex of each hexagon with each other, of each vertex of the hexagon with each other vertex in a dot-to-dot activity, you can make this shape, which you can also color in. Quite a simple hexagonal design. And if we do a more kind of internal curve stitching design, once you've shown children or students to go that far, then everybody would know what to do. And with some good fine motor skills, connecting these dots up correctly, you can end up with this hexagonal star. And once again, we can color this one in. And I've reduced this one as well, and try to pack them together in two different ways. First of all, I've packed just 4 around a central one, and then carried on packing, filling the screen with them. And I almost feel this is like an Arabic kind of a design with these curves in, and I think it's actually quite beautiful. But you can also pack them together in a different way. We can pack 6 of these shapes around the central one and carry on with this process until we start seeing almost these kind of little daisy flower shapes emerging. If we remove some of the colored ones, we can definitely see these beautiful flowers which start emerging as well. And this just happens naturally by playing in this way. If each student made one of these, you could put them together and perhaps come up with some other designs as well. Here I've packed them together and in filled space in this way as well. So that was the hexagon. So we've looked at the triangles, the squares, the hexagons, and now I'm going from 6 back to 5 to the pentagon. Now the pentagon is really my favorite shape because it lends itself to making some really beautiful, intricate designs because of the fact that it doesn't tessellate. So we'll start off just by looking at some dot-to-dot activities. If we, as we did for the hexagon, connect each vertex with each other vertex in a pentagon, we, of course, make this 5-sided or or stellated star. And we see in the middle of the star is another pentagon. So we can, of course, connect up these points as well. And now we have a star inside a star. We could, of course, carry on in this fractal-like way and maybe create a design like this. I see as quite a powerful kind of image that. So this is a 5-sided star which we've created with pentagons. And it's definitely fractal-like. In South Africa, we have some wonderful beaches. Last December, I picked up this sea anemone skeleton, and they are designed by nature to have this beautiful pentagonal structure about them. And in South Africa, we're also very privileged to have what we call the pansy shell. It's the skeleton of a sea urchin. I also picked this one up at the same beach. They were actually apparently a species that was busy being going into extinction, but they've been looked after, so more and more of them are emerging on our beaches again. Very beautiful pentagonal symmetry there. And this brings us, of course, to the Fibonacci sequence. Now, I'm sure all of us know the Fibonacci sequence. Fibonacci sequence is when we add 1 and 1 together and we make 2. And the next number in the sequence would be 1 plus 2 is 3. And 2 plus 3 gives us 5. And 3 plus 5 gives us 8. And 5 plus 8 gives us 13. 8 plus 13 gives us 21. And 13 plus 21 gives us 34. So we can carry on adding the last 2 numbers together. 89 plus 144 is 233. 144 plus 233 is 377. And so on and so forth. And very quickly, these Fibonacci numbers get very, very big. Now we've got to stop somewhere. Now I decided to stop at these 2 last big numbers. And if we take these numbers and we divide the last number by the one just before it, particularly if we go very high up in the sequence and make very high numbers, then we find that eventually this ratio starts converging to a very special irrational number called the golden proportion. And mathematicians like to give it the symbol phi. So just like we get the irrational number pi, we also have this irrational number phi. And there's also a Vedic sutra which relates to what we've done here, Antya Ureva, only the last 2 terms. And we generate this special irrational number. Now, when we look at a pentagon, we find that if you take the 2 lines which I've labeled L and B in a pentagon, whether the larger set or the smaller set, when you divide L by B, we get 1.618. So this golden proportion is actually hidden inside a pentagon. So the Fibonacci numbers are in there. That means any 5-petaled flower or those sea anemones and urchins we see have this special irrational number inside them. My favorite thing to do with a pentagon is create a pentagonal grid. Now the way you would do that is you would start off by connecting up the vertices again, getting the star, and making another star on the inside. And then what we do with the smaller star on the inside, we lengthen its sides. So if we look carefully what we do, you can easily give this activity also to your students, and you could tell them to use a ruler to make this diagram as it is now. And then you lengthen the sides of the inner star. And when you lengthen the sides of the inner star, you start seeing more pentagons. If we were to find stars inside the smaller pentagons, and then put stars inside even smaller pentagons, and then we proceed to lengthen the sides again of these very small stars. We lengthen their sides again, and then we extrapolate even further. Then we eventually end up with this pentagonal grid, which is very fractal-like in character, very mysterious. You see, if you look at this design, you see parallel lines. and the perpendicular distance between any two such sets of parallel lines will also, when you divide the perpendicular distances between them, you will get a ratio of 1.618 as well. So what can we do with this pentagonal grid? Now, I find as a high school teacher myself that when I have to teach children Euclidean geometry, there's very often very involved diagrams with circles and triangles and parallelograms, and you've got to apply your circle theorems to see what's going on inside that diagram and then analyze and do certain proofs. Now, I think that if one does the activity I'm going to show you with the pentagonal grid with children, you could stimulate them and teach them to get used to seeing or Bilocanum, observing shapes inside shapes. So how many stars can we see in this pentagon? I've colored in these stars on the vertices in the middle, one color, and then looking for some other stars, I've made these ones a bit darker, more stars, some more stars. Then I just colored in the edges and made this diagram here. And one can really, there's an infinite number of patterns one could make. I've actually had here in South Africa where I've done workshops, we've had competitions when we go to schools and do these kind of activities where the children then send in their star designs and we choose the most beautiful ones. So here's a few more things you could do with the pentagonal grid. Here's a very big one. It's just a simple way of finding stars in this grid. An infinite number of stars. This one also drew out on my husband's AutoCAD. And here's the very last one as well. Good, so one more thing about a pentagon is that the star that we've drawn inside, we could of course actually, because it's a fractal type of shape, you can go outward as well. Now, if I take this outer star and I just take one of the stellations or legs and take it off to the next slide, we can see that if we then draw the biggest pentagon we can at the top and draw a star inside it, you can actually get smaller and smaller and smaller pentagons and therefore smaller and smaller and smaller stars, which kind of zoom into that vertex at the bottom. And again, the golden proportion ratio is very evident here as well. And now let's, last thing on the pentagons is how can we paste pentagons together in a way which makes some interesting designs or patterns. And as I said before, because pentagons don't tessellate, we can make some really interesting patterns. So if you can just cut out hundreds and hundreds of pentagons and get your students to stick them together, we can see what kind of patterns will emerge. What I've done here, the central one here, I've moved to one side, and then I've packed 5 of these and made a larger pentagon. So this larger pentagon is itself made of pentagons which are made of pentagons. And we can reduce this one and put 5 of these together and we make a pentagon of pentagons of pentagons of pentagons, real fractal. We can color it in, and I've done it once more. So reduce it again, pack 5 of them around to make a new pentagon, color it in, and we see the more we do this, the more intricate the fractal spreads out. And that golden proportion is locked into the areas. You can do some maybe interesting calculations of the areas of these shapes and see where the golden proportion also emerges. This particular design we could pack together in a different way, get kind of a more just like a two-fold symmetry here. Another way you can pack pentagons is like this. You can actually pack 10 pentagons together in a circle. Naturally, they form this. And then in the middle, we've actually got a decagon, in other words, a 10-sided shape. And if we reduce this, and we put 5 of these almost circular structures interlocking together, we make, again, a pentagon. And I've just put lots of them together and then coloured them in a bit and got this quite pleasing design as well. Here's another way we can put pentagons together in a more regular way. To finish off with the pentagons, here's a pattern with hexagons, pentagons, squares, and triangles. I've actually made some interesting patterns also with heptagons, which is not such a familiar shape for us, but heptagons tend to make some really interesting patterns as well. And now we've got 2 more topics before we finished with the talk. The first topic is Penrose tilings, which is very much related to pentagons. Now, Roger Penrose is a British mathematician, and he actually won also a Nobel Prize for Physics. And he came up with this Penrose tilings, which are aperiodic tilings. And it's a way to generate infinitely changing patterns using 2 types of tiles. And these tiles we get from pentagons. The first one is the larger rhombus. And the second one is a smaller rhombus, which we get from putting 2 of the stellations of the star together. When we look at this previously made diagram, we actually see the smaller Penrose rhombus in here. Now, even that infinite leg of the star with stars inside is a half of this rhombus. And when we divide the longest side of such a triangle, which is half of the rhombus, by the shorter side, we also get the number 1.618. It's interesting, it's also 1 divided by 2 sine of 36 over 2, or 18 degrees. We can also get Penrose darts. Now, what's so interesting about these is that they are non-periodic or aperiodic tilings because they lack translational symmetry. And when you start packing them together, we actually find eventually, though they can pack chaotically, they will eventually make some 5-fold symmetry. Here's actually the largest shape as a decagon. And if you color it in a certain way, we also get this 3D, almost interlocking cube effect. Here's just, we need to get to the end of the talk. Here's some ways I've put some Penrose rhombuses together. Again, if you make a whole lot of them in a class, you don't have to make symmetrical diagrams. You can go totally asymmetrical with them as well. So here are just a few that I've put together. Really has such a 3D effect very often as well. But what starts emerging doesn't matter if you pack them together chaotically. They will eventually start showing a pentagonal symmetry as well. If you look very carefully inside this design, I haven't really packed these rhombuses together perfectly because as you see those little pink ones in the middle there, it's not totally symmetrical. So they've got this chaotic aspect about them. You can also see this decagon occurring very often in this set of rhombuses packed together. Penrose darts also make some fun diagrams. Just show you 2 of them. Another set. Good, and I even attempted to see if I could make some Escher type tessellations of these darts. So cut some bits out of them and stuck them on the other side. And we see that you can actually tessellate with them as well. And lastly, we're just going to look at, can we tessellate with 3-dimensional shapes? Now, the only 5 completely regular solids or polyhedrons are the tetrahedron with 4 triangular faces, the square with a cube with 6 square faces, octahedron with 8 triangular faces, a dodecahedron with 12 pentagonal faces, and an icosahedron meaning 20 triangle faces. So these platonic solids are actually generated by folding, tessellating triangles, squares, or pentagons into the third dimension. So the tetrahedron, the octahedron, and the icosahedron all have triangular faces. There's only one platonic solid which has square faces, the cube, and then we have the 12-faced dodecahedron, which has pentagonal faces. Now, can we pack them together and tile into volume or 3D space? And we'll just end with a few slides of looking at that, and then we're finished with the talk. So, interestingly enough, if you try to pack tetrahedrons together, in other words, these four-sided, four-faced triangular shapes, we find that although they appear to be able to pack together perfectly, they don't actually. There's a gap. There's a small gap. They don't really fit together perfectly. But as you pack them together, we start seeing the icosahedron emerging. But it's not a perfect one because they don't fit together perfectly. Almost make an icosahedron. Similarly, octahedrons, in other words, the shapes which have 8 triangular faces, also don't tile 3-dimensional space. If you try and pack them together, there's a little gap. Here's some models I've made. But as you start packing them together, we see something interesting also emerging. On the inside of where the octahedrons are packed, an icosahedron starts emerging. And on the outside, you start getting a 12-sided dodecahedron with pentagonal faces being formed. So they kind of build each other, but they don't fit together perfectly, which we can also analyze with some pretty easy 3-dimensional trigonometry and perhaps also with vector algebra. And we see that there's actually a 1.47 degree discrepancy per tetrahedron, and that's why they don't really fit together. So I wondered, can we tile with tetrahedrons and octahedrons maybe together? So what I started off by doing is taking an octahedron and pasting tetrahedrons onto its sides, and we see they fit together beautifully. We can even make a stellated tetrahedron. And to end off with, almost done with the talk, I again used my husband's AutoCAD, and he helped me design a 3D octahedron and some 3D tetrahedrons in AutoCAD, and we stuck the tetrahedrons onto the octahedron. Then we proceeded to stick on more tetrahedrons, and in the valleys, we start sticking octahedrons again, and we can fill, and they fit perfectly together. So we get just octahedrons on the outside, and then in the valleys, we can pack tetrahedrons again, and then octahedrons on the corner. And what do we see in the end? That we get a bigger octahedron made up of smaller, perfectly tessellating tetrahedrons and octahedrons. We started with an octahedron in the middle and ended with an octahedron at the end. If we keep on packing, we even can make an even larger tetrahedron. So you can tile 3-dimensional space with interlocking tetrahedrons and octahedrons. And to end with one more slide, this is a very beautiful coming together also of the golden proportion, where if you take 3 what we call golden rectangles fitted into each other as shown, and the ratio of the length to the breadth is 1.618 to 1, and we connect up the vertices, we actually make an icosahedron as well, because it of course has this pentagonal symmetry also. So that's the end of the talk. I know it was a bit long. Hope you enjoyed. If you've got any questions, or I'm very happy to email answers as well to you. Now's the time. Thank you.